Hi everyone. How are you guys doing? First of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy where every concept of physics, chemistry, and maths are being taught to you completely in English. So, the topic that we are discussing today is rigid body motion, and today we'll be talking about pure rolling. So, moving forward, before we get started with today's discussion, let me introduce myself for those of you who might not know me yet. So, my name is Rohit Dixit, and I study mechanical engineering from IIT Delhi. Now, for the past almost 8 years, I've been teaching physics for the IIT JEE exam and in the offline setups where I was associated with some of the topmost institutes in the industry. I myself, as a student, was All India rank of 447 and All India rank 192, the two stages of the IIT JEE exams that I took. I also cleared the NTC stage 2 and I was in the top 1% in the NSCP. Now, I've already coached many students to top ranks in both the IIT JEE Mains and Advanced in the online session, in the offline setups. Now, I hope to continue doing that here online with you guys. So, how can you make sure that you are getting top ranks and you are not missing out on your preparations even in this lockdown? So, this is what you can do. You can get yourselves the Unacademy subscription, and that will make sure that your studies are going ahead uninterrupted and uh, better than others also. So you will have live classes with this Unacademy subscription where you will get to interact with your educators, and these classrooms can be pretty interactive because they have live polls and they have leaderboards. Then you also have test series and analysis sessions where you are regularly checking your standing in the competition, your readiness, and you know where you're lagging and where you can power ahead. All right. Also, you have live doubt clearing sessions with your Unacademy Plus courses. So every fourth session in your Unacademy Plus is supposed to be a live doubt clearing session. So that also ensures that your doubts are never getting piled up. Hello Rajesh, how are you? All right. And on top of all of these benefits, you're also getting the chance to study from India's best educators, the comfort and safety of your home. Now, moving ahead, these are there are many courses right now which are ongoing on the Plus, which are being taken by the JEE English team. So there are three courses of class 11th, and there are four courses of class 12th. Okay, so you can choose any of these and make sure that your JEE preparation is going on track. So, how do you enroll in these courses? Very simple. First, you'll need to install the Unacademy app. Once you have done that, you go to the Plus section of your app. You select your goal as IIT JEE and you click on that get subscription button. Now, when you do that, you'll be redirected to the payment page where you can use this code RD Live, and this will help you get a 10% off on already very competitively priced subscription fees. Now, this subscription fees you will realize comes at almost 2300 per month, which is very less, and this one comes at almost 3200 rupees per month. So trust me, these fees are very less compared to what any reputed offline institute would be charging you. Any offline reputed institute would charge you anywhere between 4 times to even 10 times this fees. So you're getting the same quality education from the topmost educators at a very competitive pricing. Make sure you benefit from here. Use this code RDLive to get an additional 10% off also. And when you click on proceed to pay, you will realize that there are a lot of no cost EMI options available for any subscription which is of 6 months or more. So that will also reduce the burden of that one-time payment also. So Unacademy is providing you such great education at such nice prices. At these prices, trust me, this subscription is worth having. So go get yourselves the Unacademy subscription. And those who are following us on the JEE English channel of YouTube can connect with us on the Telegram app using this link so that you are getting all the notifications of all the lectures and sessions that are happening here on the JEE English channel, and you're not missing out on anything. Now, let's get started with today's topic. So today we'll be talking about pure rolling. So in the last class we discussed how you could analyze any general motion. Okay, and we also realized that a special case of general motion was called pure rolling, where any object in contact with the surface was moving such that the bottommost point of the object, which is in contact with the surface, does not slip with respect to this surface. That kind of motion was called pure rolling. So we will try and understand how pure rolling works and how we can analyze. Okay, so we have already talked about this, that most of the times the shapes that we are going to talk about are going to be either rings or cylinders or spheres, where the cross section would appear as shown. You will see a circular cross section when you see look at any of these shapes from the side, and you will realize that there is a single point contact between the surface and our object. If this single point is not slipping with respect to the surface below, then the motion is called pure rolling. We also realized that there were two other possibilities, which were motion with forward slipping and motion with backward slipping. Okay. We also discussed the conditions of these. Okay. And I hope you remember those. Now, let's focus on pure rolling on ground. I said when an object is doing pure rolling on the ground, then what that means is that this contact point of the object remains stationary with respect to ground, which means the velocity of this point with respect to the ground is zero. The condition for that was, I hope you remember the condition for that. Condition was that VCM would be equal to omega times R. This was the condition of pure rolling on the ground. This ensures that the speed of the point O is zero instantaneously. Okay. So now what you will realize that if you take a closer look, then you realize that the velocity of this point is VCM. If you wanted to calculate the velocities of different points, you will realize that, let's say, when I look at the bottommost point O with respect to the CM, then with respect to CM, it has a velocity which is backward, right? This is the velocity of O with respect to CM, okay, where this is the CM. So this is omega times R, and the velocity of CM itself is forward, right? So the ground frame velocity of this point O would have been the vector sum of these two. Now, since the condition already was that these two are equal, so you realize that the velocity of this point becomes zero. Okay, I hope you can see that easily. Let's draw a vector which is equal in length. So that ensures that this point is at rest at all instants with respect to the ground, right? Hello, AA, how are you? Okay. So what else can you see? What else can you see? So you can also realize that the velocity of the topmost point, with respect to Cm is like this. So this is velocity of Cm, which is omega r. This is velocity of, let's call this point some p, velocity of p with respect to Cm, okay? And the velocity of Cm itself was forward, right? So velocity of Cm itself was v. So the net velocity of this point, the topmost point, becomes 2 VCM. Okay. Now we also realize that when I want to write the kinetic energy of any system of particles, then how do you write that? You write that as half m VCM square plus half I omega square. I hope you remember this. What was this term? This term was kinetic energy of the system with respect to the Cm, and this was kinetic energy of the Cm, right? And this is how you could write the total kinetic energy of any system of particles. Now you realize what is the motion of the Cm. The motion of the Cm is translation, right? If you look at the Cm, what is your Cm doing at all points? Your Cm is translating in straight line like this, right? So this kinetic energy is also called the translational kinetic energy of the body. Now, you will also realize if you went into the reference frame of the CM, सर कभी कभी बहुत लेजी फील होता है, पढ़ने में मन नहीं करता, तो क्या करें? सो क्या करोगे यार, अपना एम याद करो और क्या. I can understand. That is, trust me, one of the biggest problems, okay, being consistent. Trust me, I think that makes a huge difference between students' performance. So most of the students, to start with, when they start with their JEE preparation, all of them are motivated, but that's the difficult part, right? Most of the students are preparing for at least 2 years or even more than that. So how do you stay motivated for such a long duration? It does get difficult, I know. It does get difficult to stay motivated towards a goal which is so far off, right? So yes, but trust me, that is what you have to do. That is what makes the difference between a successful student and student who doesn't succeed. Okay, so you make sure to keep yourself motivated. Keep yourself keep reminding yourself of the goal that you are aiming for, and you should be very, very serious about it. So the only reason why you would feel motivated is if you are really serious about getting into IIT, okay, if you really want to crack it. So make sure that you feel that way, okay? And trust me, if you can manage that, then trust me, I think half the battle is won, okay? Then trust me, cracking the JEE will not be a problem, okay? So what you can do is whenever you're feeling like that, so you can think of your goal. Maybe you can have something. You can write a sticker on the walls of your room saying, okay, this is my aim, this is what I want. You can maybe keep reminding yourself how much tough the competition is, right? So let's say you are aiming for a particular rank. Okay, so maybe you can write it on the wall. Okay, okay, I want to be in, let's say, top 1,000 out of, right? Okay, one more zero. Yeah, that is it. 10 lakh people will do this. So keep reminding yourself of the aim that you set for yourself, and realize how difficult that is going to be. Okay, so you have to keep yourself motivated. All right. And again, as I said, so you can also keep a picture of the IIT that you want to go to, maybe in your room, so that keeps you motivated. That keeps you reminding of your goal. I mean, I don't know. You can try a lot of things. Okay, so whatever works for you, whatever works for you. So something which should remind you constantly towards your aim, right? And something which would remind you that how difficult it is. So you can't afford to be lazy. All right, that's the only way it is going to work. And trust me, no matter how difficult it appears right now, no matter how you have to force yourself to study, and however you have to sacrifice and go against your own will, at the end of the day, when you do get your dream result, okay, and imagine yourself going into an IIT of your dreams, a college of your dreams, rather, any college it may be. Trust me, the day you step into that college, that is going to be the best day of your life. So I remember, I mean, preparing all the while for getting into IITs is one thing. So I had decided that I want to go to IIT Delhi, and I remember the first day that I was getting inside IIT Delhi, looking at the campus. It was an amazing feeling. So trust me, when you are there at the end, when you achieve it, everything will be completely worth it. So make sure you keep reminding yourself of that feeling. Okay, that I want to one day walk in the campus. Okay, all right. So let's move forward with the discussion then. Now, as I already said, a relation between VCM and omega is known, which is this. Now, you will also realize, okay, sorry, I was saying, yes, if you went into the reference frame of the CM, then, okay, so yeah, I think we are back online. Okay, something again keeps going wrong with my software. Okay, I don't know. Anyhow, so moving forward with our discussion, as I was saying that if you go to the reference frame of the CM, then what does the body appear to be doing? Okay, you will see that the body appears to be doing pure rotation, correct? In the reference frame of the CM, what you will see is that the body is performing pure rotation. You know the kinetic energy of that pure rotation. The kinetic energy of that pure rotation is going to be half ICM omega square. So that is why this one is also called the rotational kinetic energy. This is called the rotational kinetic energy of the rigid body. Okay. So hi Amod, how are you? Okay. Okay. Then again is this. Yeah, the stream seems a little laggy right now, right? Okay. Speed of net is fine, but I don't know why stream has become laggy suddenly. All right. Moving ahead. Now that we have discussed that this is the kinetic energy of the body that we can divide into two parts. We also realize since the relation between the VCM and the omega is this, so that also led us to see that the bottommost point O acts as an instantaneous center of rotation, right? What does that mean? That means that if I look at the bottommost point, what is the velocity of the bottommost point instantaneously? Instantaneously, it is at rest. Correct. Now, if you go into the reference frame of O, so what you will see in the reference frame of O, see in the reference frame of O, rigid body performs pure rotation. We all know this, correct? And since O is stationary with respect to the ground, so that was the condition for pure rotation, right? So at an instant, if you go into the reference frame of O, it appears that okay, the body is performing pure rotation about O, and O itself is stationary with respect to ground. So that is what I mean to say that the bottommost point O acts as an instantaneous center of rotation. So the entire body appears to be performing pure rotation about O in the ground frame. Okay, so I hope everybody can agree to that, right? So that is what I mean by this. So instantaneously, the entire body appears to be performing pure rotation about O in the ground frame, right? Now, since there is pure rolling happening, now you realize velocity of any general point. I already knew earlier we had realized how to write this. We knew you can write this as, so there is one way of writing it, which is with respect to the CM. Okay. So one way of writing this was that velocity of any point P would be velocity of point P with respect to CM plus a velocity of CM, right? So this had given us omega cross R of P with respect to C plus VC, correct? So we already studied about this. We already discussed this in the last class. Now I have another information available. So as I said, we had already discussed that any general motion can be seen as translatory motion of one point and pure rotation of the body about that point. Now, I hope you realize that the reason why we chose DCM was because it is easier for me to look at the translation of DCM. Now, in special case of pure rolling, you also know about the translation of one more point, that is the bottommost point. You know that the bottommost point in the ground reference frame will appear stationary, correct? So if that appears stationary, then I have another way of writing all the velocities. So suppose there was this point P. So there is one way which I already showed you. So you can see that that has been done here. So let's see. So here I wanted to write this. So I wrote it like this. This is omega r, omega cross r, right? Then I added this. Then I added this, ECM to this, correct? And that gave me the velocity of point P. Now, turns out there is another way of calculating the velocity of P. How? Let's see. Now you focus on the point O. If you go to the reference frame of point O, you realize in the frame of point O, the velocity of P is going to be in fact this. If this is your R dash vector, then this is omega times R dash. And the velocity of P itself is zero. Velocity of O itself is zero. So whatever is the velocity of P in the reference frame of O would be the velocity of P in the ground frame also, right? So that is the trick that we use. Secondly, I can write that V of P can also be written as velocity of P with respect to O plus velocity of O. Agreed. Because in the reference frame of any point of the rigid body, the body will be performing pure rotation. So can I say that this is omega cross R of P with respect to O, and this term is already zero. Okay, so that is what I am getting. So now I can write the velocity of point P directly in one go with the help of the instantaneous center of rotation. So that is a huge advantage I have. Now I don't have to find two velocities, vectorially add them. I can directly write the distances of every point from the instantaneous center of rotation O and multiply that with omega, and that will give me the speed of any point. You can see from here. What is the speed of the CM? What is the speed of the CM? It is omega times R, correct, which is equal to VCM. How about the velocity of the topmost point? The velocity of the topmost point, you will realize, will become, if you join this is 2R. So this will be 2 times omega R, which is essentially 2 times VCM. So you realize the velocity of every point now can be obtained in a single go. Now you realize the velocity of this point would have been this into this, like this. So now, with the help of the ICR, the instantaneous center of rotation, you can write the velocities of different points in one go. Okay. So how about the acceleration? Now you realize the ICR doesn't really help you much with the acceleration. So though the velocity of ICR is zero, is the acceleration of ICR zero? Think about it. Let me know in the chat. Is the acceleration of the ICR zero or not? What do you think? Okay, so tell me your thoughts about the acceleration of the ICR. Does the point O, which is the ICR, which is essentially instantaneous center of rotation? Okay, why are we calling that instantaneous center of rotation? I just explained to you in the last slide that at any instant the entire body appears to be performing pure rotation about that point, right? So ICR, which means instantaneous center of rotation. My point was instantaneous center of rotation obviously is stationary, right? But what about its velocity with respect to ground is definitely zero. But what about its acceleration? So tell me, is the acceleration, again, whenever I'm talking up now, I'm talking in the ground frame, is the acceleration of the ICR in ground frame zero? Is it zero or not? Okay, come on, try and give an answer. Good evening, Mahiji. So, what do you think? Is the acceleration of the ICR in ground frame zero or not? Yes or no? Give me a yes or no answer. Think about it. Try and give your answer in yes and no. What do you think? Right? Anyone? Does anyone want to give this a try? Good evening, Aftab. How are you? All right, guys. So try and answer this also. Okay, so everybody is just saying good evening, but nobody is trying to give the answer. So, what do you think? Is the acceleration of the ICR in ground frame zero or not? So, APA, Mahi, Aftab, anybody? Any idea? Okay, all right. So that is so weird. The moment I asked you to guys to answer, I saw suddenly, suddenly the live viewers, decreased. Okay, which is weird. All right, so you guys don't want questions to be asked of you or what? Come on, let's keep this interactive. Try and answer. What do you think? Okay, well, so since nobody is giving the answer, I might as well say it. So let's get rid of all the notations that we had so far, and let's see. Okay, so I don't know. Should I wait for someone to answer? Uh, okay. Right. So the answer here, of course, is no. So the velocity of the ICR is definitely zero with respect to the ground. However, the acceleration of the ICR is not zero. Okay, so S Pandey says yes. So no, no, no. That is not the correct answer. The correct answer is no. Why? Think about it. Think about it. Do we know the acceleration of the CM? What do we know about the acceleration of the CM? So look, CM is moving in a straight line. We already discussed this. So CM will be moving in a straight line. It will be translating like this, correct? Because this is a rigid body. So rigid body cannot change its radius. So when it is performing pure rolling, you realize that this CM would be moving in a very straight line. So you realize this CM can only have an acceleration in the x direction. I hope you realize if I make these my y and my x axes, can I say that ACM in y direction can is always zero? Okay. So ACM y has to be zero because CM cannot go up nor can it go down, right? So the acceleration of CM in y direction is zero for sure. I hope everybody agrees to this. Okay. Now, in the reference frame of the CM, what is the acceleration of O? Acceleration of O is vertically upwards and it is omega square r. So it is non-zero. Why it is having such an acceleration? Because in the reference frame of the CM, it is rotating, right? In the reference frame of the CM, you will realize that point O is rotating in a circle of radius r. So this is the acceleration of O with respect to the CM. This is the acceleration of O with respect to the CM, even if alpha is zero, by the way. Even if alpha is zero. Again, another condition. Let's talk about another condition of pure rolling, which I think I did not mention here. Yes. So conditions for pure rolling. Let's just write it here. Conditions for pure rolling on ground. What were the conditions of pure rolling on the ground? Now, those conditions were one, PCM equals omega r at all instants. Now, if that is supposed to be the case, you realize if I differentiate this, I will also get that ACM equals alpha r. So these are the two conditions of pure rolling on ground or any stationary surface. Okay, correct. So these are my two conditions. Remember that. Very, very important. So if I wanted to take a look at the accelerations of this point, so here I can already see that the two velocities, omega r and v, are cancelling each other out, correct? Now, how about the accelerations? Acceleration of CM, let's say, is in this direction. Let's assume that it is in this direction, ACM. In the reference frame of the CM, what acceleration does the point O have? The point O has an acceleration, two accelerations in fact. Okay, so one is omega square r and another. Okay, so let's write those with some other color. So this is the acceleration. This is the acceleration of O with respect to the CM. One this and one may be this. So omega square r and alpha r. Correct. So if ACM is there, alpha has to be there. So in the reference frame of the CM, the point O will have two accelerations, one centripetal acceleration and another tangential acceleration due to the alpha that the body has, right? In the reference frame of the CM, you will see that the body is rotating. So rotating body has to have a centripetal acceleration, and since there is alpha tangential angular acceleration also, so it will also have a tangential acceleration. Now you add to this the ACM. If to find the net acceleration of this in the ground frame, you will also add ACM to this. Now, what you will realize is that these are the three accelerations that I can see this body having, right? So in this particular case, these two will cancel each other out. The alpha R and the ACM cancel each other out because they are directed in the opposite directions. However, you still have one acceleration left, which is omega square R. So Shiva, when the Deshin says your teaching is awesome, sir, and you are so underrated, but if you teach in any other Hindi channel, you will win hearts of millions of students. All right, Shiva. So thank you for the compliment, and don't worry, don't worry. So I had never taught online before, right? So I have always been teaching offline. So I guess it takes time for people to get recognition online. So it's okay. Don't worry. And thank you for the compliment. In any case, all right. So yes, I have been teaching, in fact, in Hindi in all my life. So past 8 years, I have been teaching in Hindi only. But here, I thought this was a new opportunity to teach in English, something which I had never done. So yes, this is a new challenge for me. So I was excited for a new kind of challenge also, and I wanted to also help students who have a problem with understanding Hindi. Okay, so yes, of course, as you know, most of the content on YouTube is available in Hindi only. So, Unacademy wanted to think about students who are not very comfortable with Hindi and wanted content in English, right? So that's what we are trying to do. And don't worry, I think it just takes a little bit of time online. So thank you so much for your wishes, by the way, and I hope so too. I hope so too that in some time, we will get enough recognition. This JEE English channel will also get enough recognition and support from you students. You already show a lot of love, so thank you so much for that. That is quite encouraging. All right. Yes, yes. So it's about that also. So don't worry. But there is so much content. I don't know. I personally believe that the content will not be saturated. I don't know. There are so many details that you are often overlooked. While explaining things. So don't worry, and let's see how this English thing goes. And maybe you don't know. Maybe in future I will also try teaching in Hindi also. Okay, so I would be glad to do that as well. But right now, let's just focus on this channel. We want to grow this channel. We want to help every student who is not really comfortable with Hindi and wants to still learn the best of the concepts. Okay. So ARJ says, sir, is rotational mechanics possible with knowledge of NLM as it carries huge weightage in mains? So ARJ, for rotational mechanics, that is the problem. You need all the knowledge before this chapter. Not only NLM, you will need, okay, how do I tell you this? So you do need NLM, you do need your work energy methods because you'll be using those also in analysis. You do need your momentum and impulse momentum theorems, everything. So you do need all these topics. Okay, you also need to know the kinematics of circular motion, dynamics of circular motion. So everything is used in rotational mechanics, and that is why this is the favorite chapter for any of the competitive exam makers. right? Not only for mains ARJ, it carries a lot of weightage in advance also. The reason for that is in one good question of rotational mechanics, all these concepts can be tested. Your examiner can test all the knowledge and understanding of all these concepts. So that is why they love asking questions from rotational mechanics. Okay. So my advice, no, only NLM is not enough. You should have a good command on all these topics. Okay, if you want to be good at rotational mechanics. So I hope everybody figured that the net acceleration of point A, O with respect to ground would be upwards and it would be omega square r, right? So as I was saying, so we want to write the acceleration of any general point. So acceleration of any general point, again, we will realize we already knew this. We already knew this, that acceleration of any point P with respect to ground would be acceleration of point P with respect to CM plus ACM, right? This we realized had two components, one centripetal acceleration, one radial acceleration, tangential acceleration. So this we already knew was R of P, so alpha times R of P with respect to C plus, I had minus times omega square R of P with respect to C, and I have plus ACM. So there were three things that I had to write. So again, let's take a look. So this vector diagram easily shows you about the velocities, but let's have another vector diagram which shows you about the accelerations also. So how about the accelerations? So maybe we can draw ourselves another sphere. Okay, because yes, here also there is a lot of markings. So maybe we can add a page, and let's see. All right, so let's draw ourselves another rigid body, which is like this. Okay. And it is very important for you to see this diagram and visualize how you get the acceleration. Okay, trust me. So again, let's mark different points. So imagine this is my point O, this is my point O, this is my point C, which is the CM of the body. I'm assuming that this body is a uniform body. So the CM lies here only. Okay. If this was non-uniform, then yes, the CM could have lied somewhere other than the geometrical center. But if these bodies are uniform ring, uniform cylinders, uniform discs, uniform spheres, they all have their CMs coinciding with the geometrical centers only. So that is the assumption that we are making here. Now think about this. Think about point number P. Now point number P has two accelerations with respect to the CM. So in the reference frame of the CM, you realize this body has this acceleration alpha and it has an angular velocity omega. This also has CM is also translating with VCM and has an acceleration ACM. Correct. So in the reference frame of this C, you will see two accelerations. Correct. You would have seen a centripetal acceleration, which is directed like this, which is omega square r of, let's not, capital R, small r of P with respect to C. Then you will have alpha r, which will be like this, in alpha times small r. Correct. So these will be the tangential acceleration and the centripetal accelerations that you can see. And of course, you will add to this the ACM to find the ground frame acceleration. Add to this ACM. So vector sum of these three would have told you the ground frame acceleration of P. Okay, I hope you can realize that. So in the reference frame of the CM, it has one acceleration which is the centripetal acceleration directed towards the CM. It has another acceleration which is the tangential acceleration directed perpendicular to this line. And so this is the net acceleration in the reference frame of the CM. To this, you add the reference frame, the acceleration of CM, and you get the ground frame acceleration, right? Now, suppose if I wanted to find the acceleration of O similarly, I told you the acceleration of O, how much was that? In the ground frame, you would have seen omega square r. Okay, in the reference frame of the CM, you would have seen this, and you would have seen this alpha r. And then you would have added to this the ACM, and you would have realized that AC and alpha R would have cancelled each other out because they are equal in magnitude, opposite in direction. So these two cancel each other out. So the acceleration of O comes out to be omega square R. All right. Now imagine if I wanted to write the acceleration of P with respect to O, okay, with the help of O. Can I do that? Of course, I can do that. And how would I do that? Again, I will go into the reference frame of O. In the reference frame of O, I would have seen that P has two accelerations, correct? So let's talk about here. This O is here. So this P would have had two accelerations, one directed here, and this is P. So this would have been, this acceleration would have been omega square R of P with respect to O, correct? This is what would have been the centripetal acceleration from the reference frame of O. Then you would have had another acceleration which would have been like this. It would have been alpha times R of P with respect to O. And then to this, you would have added the acceleration of O itself, that would have been in this direction. Okay, omega square capital R. So the vector sum of these three would have given you the acceleration of P from the ground frame. And yes, turns out it will come out to be equal to this. Turns out this, okay. Turns out that this, the sum of these three, would in fact come out to be equal to this vector sum of these. Okay, so yes, you can write the acceleration of point P also with the help of O, but you do realize that does not decrease my calculation. I still have to add three vector terms. Okay, so that really doesn't help you much. Okay, so let's write that here in any case. But you realize it had a clear distinct advantage when I wanted to write velocities from the reference frame of P from O. Okay, hello Arun Kumar, how are you? So there you realize I just had to calculate one term compared to two terms here. However, in finding the acceleration, the fact that O is the ICR does not help me much. I still have to find three terms. Acceleration of P can also be written as acceleration of P with respect to O plus acceleration of O. So here, please realize that this is a major or common, very common mistake that a lot of students make. They think that acceleration of O is zero. No, that is not the case. Acceleration of O is not zero. Please remember that now. Okay, this is alpha cross R of P with respect to O minus omega square R of P with respect to O plus, let's write omega square R J cap. J cap. Since I had taken this as my Y, this as my X, so omega square R J cap is the acceleration of O. Okay, so I need to add this. So this is how I would have found the acceleration of any general point. So you realize, so we already talked about finding the velocity and accelerations of any general point earlier in rigid body. Now in case of pure rolling, I have another method. So that is one advantage of pure rolling. That now I have an alternate method of looking at things. I can, as I said, for analysis purposes also. For analysis purposes also, I told you initially that how we want to approach the analysis of general motion. We want to analyze the translation of one particle and we want to analyze the motion of the body in the reference frame of this particle, right? So we chose C because judging the translation of C was the easiest. Now, in case of pure rolling, judging the translation of another point is very, very easy. So at any instant, the bottommost point is obviously going to be at rest, and in the reference frame of that bottommost point, the body is going to perform pure rotation. So now I can break my analysis into analysis, rotational analysis about O, and then finding everything with respect to O. Okay, so let's see. So analysis using again laws of motion, we had learned that these are the tools that are available for us for analysis. So if I wanted to analyze the motion of CM, I could have used summation fx external equals m ACM. Then I could have used Then I would analyze the motion of rigid body in the CM frame. That would have been summation of tau being equal to I alpha. Finally, now I have another alternate. Another alternate is available to me, that in this case, the analysis can also be done about the bottommost point. So how that happens, let's see. Now let's try analysis of motion about the bottommost point. So let's assume that I have been told that the body is performing pure rolling. That has to be given to me. Okay. So let the body be performing pure rolling and now let's say it has some force acting on it, and let's say it is moving under the influence of a force which is acting maybe here. I don't know. Let's draw the force anywhere. So under the force F. Yeah. Under the influence of force F. Then what are my aims? My aim was to find ACM and my aim was to find alpha, right? If I can find both those things, then I can find you anything. Right? Now, can I do that easily from here? Now, what I can say is that I can go into the reference frame of O. Now, you need to realize one important thing as well. So, if I go into the reference frame of O, so I need to write all the torques. Now, I told you that if you go into a non-inertial point, so you need to write pseudo torques also. So, this is one thing that people don't realize, that O is a non-inertial point. Okay, a lot of people mistakenly think that O is an inertial point, and that is why you can use in the reference frame of O tau equals I alpha equations. No, that is not the case. The case is because of another factor you can use this. Okay, so I'll tell you what. So in the reference frame of O, first of all, what do you see, that the rigid body is performing pure rotation? All right, rigid body is performing pure rotation about an axis passing through O. Correct? About an axis passing through O. So that is should be clear to everybody. So there is an axis which is passing like this, and the entire rigid body appears to be performing pure rotation about this. So if it is performing pure rotation, so I know for pure rotation I can use tau equals I alpha equations. Yeah. So therefore, summation tau equals tau about O equals I about O alpha can be used. Okay, so a lot of people will leave it there. That yes, it can be used. However, I want to tell you one more thing which you don't realize. Okay, it because the equation works. That is why you don't realize this. However, O is non-inertial. Why is O non-inertial? Because I just discussed that O has an acceleration, right? So O is non-inertial because it has an acceleration. So I need to include the pseudo torque. Therefore, pseudo torque needs to be included. Correct? Now you will wonder that okay, that is so weird because I never included any pseudo torque in my approach and my calculation. If that is you have tried these questions. So yes, you never used any pseudo torques. Why? Think about it. The very reason you do not use pseudo-torques was because you were always analyzing uniform bodies. Okay, and what happens to uniform bodies? In case of uniform bodies, I told you that the center of mass coincides with the geometrical center. So let's say, what is the acceleration of O? The acceleration of O was like this. It was omega square r. So in the reference frame of O, what is the pseudo force? The pseudo force I had told you acts on the CM. The pseudo force acts on the CM, and it would be this, the square r. So these will be the two forces apart from mg and n that you will see acting. So hello Vedant. So if you try to see all the forces acting on this in the reference frame of O, if you are trying to make the FBD, then you will have one N. These are the forces that you would want to mention. You have an N, which is essentially acting from here, and then you have an mg also. You have mg also. So these are the four forces that you see. Also, you may or may not have any friction. Correct. All right, Vedant. You also may or may not have any friction. So let's assume there is friction also. Now I am not sure about the direction of the friction. So what happens is that I am going to assume some random direction to the friction. Let's assume that it is backward. It may be backward. It may be forward. It may even be zero. Okay, so those are the possibilities. But I'm assuming right now it to be backward like this. Okay, so these are all the forces that I can think of to be acting on this body performing rolling, right? Can you think of any other force than other than these? So there is this F, which is the external force that was acting. Then there will be the normal reaction from the ground. Then there will be the weight of the body. Okay, so let's use small m here also. If I've used small m there, let's stick to the same kind of symbols. Okay, and this is the pseudo force. This is the pseudo force acting on the CM in the reference frame of O. Why? Because O itself had an acceleration of omega square r. Now you're lucky enough that this pseudo force is passing through point O only. And we know whenever a force passes through a point, then it cannot produce any torque. So you realize that in this particular case, about O, the only force that can produce a torque is F. Okay, so even when you were calculating all the torques, you were calculating all the torques. Now, even if you had ignored this, it wouldn't have made much of a difference because the torque of this pseudo force is already zero. That is why you got your answers all the time, even when you did not include that pseudo force or pseudo torque, right? Because that pseudo force produces zero torque. Okay, that is the advantage of such shapes. If the shape would have been non-uniform, then you would have had run into trouble. Then you would have figured out that your answers are coming incorrect. Okay, so let's add a page and elaborate on that. Add a page here and elaborate on that slightly. What am I trying to say? What I am trying to say is that, okay, very, very important point that we observe. Now, even though, even though O is a non-inertial point, the pseudo torque, the pseudo torque about it is zero. Okay, for uniform objects, for uniform objects, right? Why? As the CM coincides with the geometrical center. Okay. If that was not the case, if the CM did not coincide with the geometrical center, you would have run into trouble. You would have had to add that pseudo torque. Okay, so hello Vishnu Dev, how are you? So please remember this. You were only getting away with all that because the CM coincided with the geometrical center. That is why you never bothered about the O point being a non-natural point and not including the pseudo torque also did not matter. Now, in case, and this is going to happen only in advance. So in mains, it is very unlikely that they will ask you a question of a non-uniform object which has an off-centered CM. But in advance, they can ask you this. They can ask you of, let's say the case was, let us say that hypothetically, let's take an example. So let's discuss an example where the CM would be off-centered and where you would have had to take that pseudo torque. So let's say you have a mass, you have a ring of mass m and radius r. So uniform ring again. Imagine a uniform ring of mass m radius r. Okay, so small m comma r. Let's say that is how it is placed on a ground and it is performing pure rolling. However, you have another point mass attached to it. Let's assume there is a point mass attached to it, this small m. And at any instant, let's say it is moving. That's that. So here you will have a lot of trouble. In fact, you will realize that you will run into a lot of trouble the moment such a question arises. And that is why it is very unlikely that such a question will be asked in mains, and it is more probable that such questions would be asked in advance. So imagine, where will the CM lie? The CM would have lied somewhere here. Okay, the ring's CM lies here. The other mass is lying at the edge. So the total CM of this configuration, realize this is where the CM would have lied. Okay, this is where the CM would have lied. Now, what is the condition for pure rolling? Would that be VCM equals omega r? No. That would still be, let's say, with the center, and let's give those points some name. So let's call this O. This is my CM. So how do I denote the center? I have used O and C both. So let's call the center some dash. So the velocity of C dash would be V. I know that C dash will translate. Only C dash will translate. Now, how about the CM? CM will not just translate like this. Will not translate in a straight line. C dash would translate in a straight line. Your C would also move in the y direction. So in this case, your N and mg also would not be equal, by the way. Would not be equal. Okay, so a lot of things will go weirdly wrong here. The moment you start thinking about, so think about the situation. Imagine that this guy is moving with V. This C dash is moving with a V, and the body is rotating about C dash with respect to C dash with omega. Then you realize the condition for pure rolling here would be condition for pure rolling will still be equal to V equals omega r, where V is not the velocity of the center of mass, but the velocity of the geometrical center. Okay, that will be your velocity condition for pure rolling. Now, if I wanted to make an FBD, how will the different forces act? Let's draw an FBD. So I would have had mg here. I would have had some normal reaction coming out of here. I could have had that external force which I had used in the last question. So maybe I have another F which is acting at some random point here. And then I would have had some friction. Let's say the friction is acting here. Now, in the reference frame of O, I will need to add the pseudo force. And how and where will I add the pseudo force? I will realize that the acceleration of O with respect to ground is like this, omega square r still. So the pseudo force of this would be applied at C, the CM, not at C dash. The pseudo forces, all pseudo forces are always applied at the CM. Okay, remember this. So the pseudo force will be applied here. You would have had m omega square r, which would be F pseudo. Now, when you're taking the torques about O, okay, so now imagine you are taking torques about O. Now, N obviously does not produce any torque. Friction does not produce any torque. You have to still take torque due to three forces. Okay, so which three forces? Due to F, to mg. Now, because mg is acting shifted. Okay, one more thing. One more thing. Let me just correct this. So yes, this will be 2 mg. This will be 2 mg because there is m mass here and m is the mass of the ring. So the Cm will have a mass of 2m. Similarly, the pseudo force will also act on the Cm. So it is 2m omega square. So let's just quickly correct those, or you believe something wrong. Okay. So these are the forces, and you will see that three forces will produce a torque. And here is the problem. Here, in this kind of case, you may have missed this. So such questions, trust me, have been asked in advance. And the reason why a lot of people get this wrong is because they don't realize this, because you don't see such a case very often, right? You don't see such a case very often where the CM is off-centered. And that is why you never used to take the pseudo torque, because the pseudo torque was never produced. And you never realize that there is a pseudo torque you should have taken. And it is coming out to be zero. That is why you're not taking it. But so keep this in mind. Keep this in mind. If your CM is off centered, and then when you're taking torques about O, do remember to keep into account the pseudo torque. Okay, very, very important. So as I said, however, this. So I could have written here, I could have also written the summation of all taus, so summation of all torques about O would be equal to tau about, okay, so I've already written that. And I would have gotten away even without writing the pseudo torque, right? So even if I did not include the torque of this is zero. So tau pseudo about O in this case becomes zero. That is why I did not need to include that here. I only included all the real torques about O, and I could equate that to IO alpha. Okay. Here, if I wanted to use tau equals I alpha equation, here I should have used all the torques. Here I would have written summation of, or write those three terms individually. So tau of mg about O plus tau of f about O plus tau of f pseudo. And that would have been equal to IO times. Okay, so remember, this is how you would have gone about solving this problem. If the CM was off-centered, you would have included this. This would have been non-zero. Okay, you would have had to include this. Okay, this is an example where the pseudo torque is non-zero about O. All right, keep this in mind while solving your problem. Most of the times, you can ignore it because the CMs would coincide with the geometrical centers. If they don't, then do remember to add this. All right, now let's see what are the methods that we have for analysis of pure rolling. So we have these methods available to us. So I know there is Newton's laws approaches. So as I think ARJ was saying, can he just study rotation from by after knowing Newton's laws only? So no, you need all this because we will use all these methods. So I will use Newton's laws. How am I using Newton's laws? I will use F equals ma equations, summation F equals ma equations, and the analog of that, which is summation tau equals I alpha equations. So these are the kind of equations that I'll be using for my analysis. Then I may be using work energy approaches again. Either I may use energy conservation or I may use work energy theorem. We already know how to write the kinetic and the rotational energies. I hope you remember that work done by a force was integral f dot ds, right? So that is how you used to find the work due to a force. How about the work due to a torque? Work due to a torque is found as integral of tau d theta. Remember that you can also find the work done by torques and then use work energy theorems. Okay. Then you have momentum and angular momentum conservation approaches. And finally, you have the impulse and angular momentum approaches. Okay, so P conservation, L conservation. So these are different tools that I have. I can use any of them in my analysis and analysis about ICR. This is the latest tool that we have acquired. I can so all this while I'm doing all these initial methods. So in all these initial methods, what I'm trying to do is let's so from here to here, you will realize from here to here, I will usually try to find I'm trying to analyze the motion of CM and motion with respect to CM. So we are trying to analyze the motion of CM and motion of rigid bodies with respect to CM. Correct? In all these approaches, that is what we are going to try to do. As I said, every time you are analyzing any general motion, this is the general approach that that motion can be broken into two categories. One, motion of the CM, translation of the CM, and then pure rotation about the CM. So the top four methods would usually try to find out something about the motion of the CM and then the motion of the body about the CM, and then of course you could have used any of those approaches about the ICR also. Okay, here you would have tried to analyze the motion of every particle or the body with respect to the ICR, the instantaneous center of rotation. You already know that that is at rest. So let's see how we can analyze this. Let's use some examples. Okay. So again, I had initially also told you that there are three possibilities of motion of any body like this. Right. I hope you remember that the possibilities were pure rolling. So there were three possibilities, right? Talked about this. So three possibilities were pure rolling, then you had forward slipping, and then you had backward slipping. Correct? Okay. Now let's try and see if a solid sphere of mass capital M and radius capital R is hit by a Q at a height h above the center. For what value of h will the sphere roll without slipping? And then we will also try to analyze that what will our cylinder do for other values or sphere do for other values of h. So let's try and find out. So let's see the Q. A Q is essentially a stick. So you are hitting your solid sphere with a stick. I don't know if those of you who have played pool, you know that the stick with which you hit the pool balls, that is called the Q. Okay, so that is called the Q stick. Okay, so let's try and analyze. So let's imagine that when you struck this ball, it you imparted some impulse J. Okay, so let's think of it like that. Let's try and draw ourselves this. So let's say you hit it. Okay, and there was some impulse J imparted to it. It's some J here, and this is at a height h above the center, right? Imagine here is your CM. Correct. Now, do you realize when this impulse is important? Is there any other impulsive force that is acting? Is there any other impulsive force that is acting? No. If you talk about the forces that are acting on this sphere, so there is mg, then there is F, friction. There may or may not be friction. But you realize since the N is non-impulsive, so even if friction is there, it will be non-impulsive. Okay, I hope remember that we talked about this. That when can friction be impulsive? Friction is only impulsive if N is impulsive because F is equals mu N. So if N is not impulsive, if N has a finite magnitude which is equal to mg, then mu N, the limiting friction also has a finite magnitude. That means that friction cannot be impulsive. So since J is the only impulse, I can say that since J is the only impulse, therefore, can I say after this impulse, I will assume that the CM starts to move with some velocity VCM to VCM, and then it starts also to rotate like this with some omega. So I'm assuming all this. Now you will realize one thing. The first thing that I can clearly write is so therefore J would be equal to if this object had some mass m and some radius r. So let's assume that this body had mass m and it had radius r. Okay, that is the characteristic body. Okay, so let's imagine. Can I say from impulse momentum theorem that J would be equal to m times VCM? Right. This is impulse momentum theorem. Correct. Impulse momentum theorem has told me this. Now, if I take all the angular impulse about the CMC. Okay, so let's mark all those points. So again, let's mark this point O, this point C. So taking angular impulses about C, what I will get. So taking angular impulses about O. So the only angular impulse would be produced by J because that is the only impulsive force. And I hope you remember that angular impulse was R times linear impulse. Okay, I hope you remember that. This is what we had discussed. So the angular impulse about C of J would be J times H, correct? And that J times H will be equal to delta L, the change in angular momentum. So can I say that that will be ICM omega minus zero? Because initially the angular momentum was zero. In the CM frame, so this is since we are taking okay, so angular impulse is about C. Okay, what about since I am taking everything about C. In the reference frame of C, the why did I choose the reference frame of C by the way? Why did I choose the reference frame of C? Think about it. Okay, I will give you a little hint. Okay, so first let's complete this equation. First, let's complete this equation. I hope you agree that in a reference frame of C, this is the impulse that angular impulse that J is producing, and that would be equal to the change in angular momentum. And angular momentum about this in the reference frame of the CM initially would have been ICM omega, and sorry, initially would have been zero, and finally would have been ICM omega. So this is my second equation. So this is my equation number one, and this is my equation number two. Correct. Now, okay. First of all, let me add a small question, a small trick question. Small trick question is that is C an inertial point or not? Is C an inertial point? Think about it and tell me. Is C inertial? When I say inertial, I mean during the during the impact, of course, during the time in which the impulse J was being applied. So when it was hit during the duration of the impact, duration for which it was hit by the stick, is it inertial? Yes or no? Try and give me an answer. What do you think? So, okay, so there is a lot of discussion and a lot of serious discussion in my lectures, which I don't know. Does it may appear heavy to some. Okay, so some people may say, okay, sir is going on teaching and teaching and teaching so much, and I'm not I'm not able to follow it all the time because there is too much teaching happening here. Okay, so yes, I agree sometimes. Well, there is too much teaching happening here, but trust me, that is what you need. Okay, I don't like wasting your time because your time is precious. Trust me. Okay, so even if there is too much teaching happening, you can maybe keep pausing the video when you're watching it. Maybe you can watch it again and again to understand the concepts better. But my idea is to tell you everything. There is so much to be told. There is so many things that I don't know. I become conscious as a teacher that what if I miss this? What if I don't tell you this? What if I forget telling you about that? So that is why I keep telling you stuff all the time. Okay, so I hope you guys can bear that. And so that is why asking questions in the middle, I think, serves to take small breaks also from that discussion. I don't want you to be just thinking about and following everything that I'm saying all the time. Sometimes take a break from following me, use your own brain for a bit, try and answer this. So, do you think C is an inertial point during the impact? So, let's not only just keep on analyzing things, let's also take small breaks to think about things. Okay. Do you think C is inertial during the impact or not? So anyone can try and answer this. What do you guys think? Let me know. Is C inertial during the impact? See, I'll tell you why I'm asking this. I'll tell you where I'm going with this. But let's first think about this. Okay, the problem with rotation is that there is so much to think about, and you may miss these small little things, and that is where people go wrong. Okay, so that is why I want to keep you, completely your brain completely active. You should be thinking about every possibility, everything. Wait. I was taking the angular impulses about C, but let me just check if C was inertial or not, or did I miss something? So trust me, you will have to be that attentive while solving rotation problems. Otherwise, you will miss something. Okay, and that will uh, result in you not getting the answer and you feeling frustrated. Okay, I studied so hard, but I just can't seem to solve rotation problems. I know a lot of students feel that. The point is not that they did not put in enough effort. The point is that they keep missing out small things. There is so many small little things that you need to keep in mind. You need to be alert about. Okay, so hurry up and tell me, is C inertial? Just to ensure that we're not missing out on it. Is C inertial during the impact? Quickly tell me. Quickly tell me. Okay, anybody? Okay. So I don't know. Let me just wait for a minute at least. Come on, guys, think about it and try an answer. Just think about it and try and give me an answer. Yes or no? Yes or no? Is C Inertial is the point. See, inertial during the in the duration of the impact. Is it inertial or not? Yes or no? Think about it. Okay, so so many people watching, not one responding. Okay, so have you guys just dozed off to sleep? I don't know. Okay, nobody wants to try. All right, so let me explain. The answer is, of course, no. No, it is not. Okay. Why is it not inertial? Think about it. Think about it. What was the speed of C before, right before the impact? It was zero. After the impact, right after the impact, it has some speed VC, which means it must have accelerated during the impact. Okay, I hope you guys follow that. That let me write this. So let's write a note here. Some he was at a rest. Was at a rest just before impact and moves with VC just after impact. Right. Therefore, it must have accelerated during the impact. Can I say that? Therefore, it must have accelerated during the impact. Right. So why did I not take the pseudo impulse or impulse due to pseudo force? So first of all, will the pseudo force produce any impulse? Another important question. Will the pseudo force produce any impulse? So turns out yes. Why? Because that pseudo force would be impulsive. Why? In negligible time of the impact, the velocity has changed by a finite amount. So you realize acceleration would have to be tending to zero, and a would tend to infinity. Acceleration would tend to infinity, in fact, because in t tending to zero, it is able to produce such a change in speed, right? Therefore, the pseudo force must be impulsive. Pseudo force tends to infinity and is impulsive. So the pseudo force that we will talk about would be ma. If a tends to infinity, the pseudo force tends to infinity, which must be impulsive. However, the good thing is that we are taking the thoughts about C and all the pseudo force would have passed through C itself. Okay, so that is the only saving grace here. Okay, you have F pseudo during impact acting like this, which will not produce any talk about C, and that is why I did not bother about it. And that is why it is very important to take angular impulses only about C. If you because you could have imagined, why am I not taking the angular torques about this point? Maybe I can try taking angular torques about this point. Maybe that will also work. No. Here, beforehand, you don't know whether it is pure rolling or not. It could have pure roll, it could have forward slip, it could have backward slip. So in case it was forward slipping or backward slipping, this point would have also accelerated. This point would have been non-inertial. However, the pseudo force of this non-inertial point would have acted on C, and that would have produced a pseudo torque about this point O, which you could not have included easily. Okay, and that would have been an issue. That is why always, when taking angular impulses And when doing most of the analysis, always take thoughts about C, because even if C is inertial, as long as it is, even if it is non-inertial, then all the pseudo forces pass through this, so you don't have to ever worry about pseudo torques. Okay. Now, from these two equations, what I can say is, therefore, from here I can say omega equals JH over IC. Correct. From the first one, I could have also said also C equals J over M. Now, now I will have three conditions. If PC is greater than omega r, which would imply that J by M is greater than omega into r, which is JH over IC times r, then you would assume that there would be forward slipping, which means if H was less than ICM over MR, then there would be forward slipping. Okay, if the height at which the impact was made was less than ICM over MR, then there would have been forward slipping. Similarly, if PC is less than omega r, the condition for that would have been that J over M would be less than J H over ICMR. So I can say that if H is greater than ICM over R, ICM over MR, the motion would have started as backward slipping. And for the special case, if VC equals omega R, which means if H equals ICM over MR, then we have seen pure rolling. Okay, so this is the condition. So this is what has been asked of you, right? At what value of h will the sphere roll without slipping? At the value which is in general. So this is what I found for general. In general, if h is equal to ICM over MR, then the body will start to perform pure rolling. Okay. So let's write that value for different purposes. Let's write here h for pure rolling just discovered is ICM over MR. So for a ring, will be ICM is MR square over R, that is R. For disk, the ICM is MR square by 2 over R, so that is R by 2. At H, the height above the center has to be R by 2, and the disk would have started pure rolling. Okay, similarly for sphere, for solid sphere, how much will that be? The ICM is 2 by 3 MR square and over R, so it is equal to 2 by 3 R. Okay. For hollow sphere, again, let's write one last hollow sphere. Okay, so I think I wrote the other way around. So solid sphere was 2 by 5 MR square. So 2 by 5 R, and it will be 2 by 3 R here. Okay, so I hope you realize what I am trying to do in this question. We realize that if the impacts happen at such heights, if you took a body and gave the impact at different heights, different bodies would have started their motion with pure rolling, with the condition that VCM would be equal to omega R. Okay, so yes, enough of the discussion for the day. This is where I would like to wrap up for today's discussion. We will carry forward our discussion. We will be solving a lot of problems to understand all the concepts better. to make sure that you are closely following this particular lecture series that is of rotation, because this a chapter can be really really tricky. So as I keep telling you, every class I will show you some things that you miss, or would have missed for sure during your studies, which you miss very often because more often than not this is not used in your questions. So you can solve your easy questions still. You can still solve the NCERT questions maybe easily. Maybe you can even solve some of the mains questions easily. But when it comes to slightly tougher problems, then you get stuck because of so many considerations. So make sure that you are watching this series very closely. Make sure that you are noting down those things where you usually go wrong. What are the small things that you don't pay attention to? And then if you do all that with some practice and some uh, careful analysis, you will be fine and you will never have any problem of your rotation. There is a lot of discussion with that I had planned. But anyways, I'm glad that I'm taking it slow and I'm discussing everything in details. Okay. So, however, that is where I would like to wrap it up for today. And before I take your leave, let me remind you this is how you should be getting your Unacademy subscriptions if you haven't gotten them already. So, you need to go to the plus section of your app, select your goal as IIT and click on that get subscription button. That is how easy it gets. When you click on the get subscription button, you will be redirected to the payment page where you will realize that already this pricing is very, very competitive compared to any pricing of any offline institute. You can further use this code RD Life to get an additional 10% off, and you also have no cost EMI options available for all subscriptions of 6 months and above when you press this proceed to pay. So what are you waiting for? Get the subscriptions, and then you can even enroll in these courses which are ongoing currently and are being hosted by the JEE English team. All right, so three courses of class 11th, four courses of class 12th. And now, if you like this video, then yes, don't forget to press the like button. Trust me, that gives your teachers and the Unacademy team a lot of motivation. That is the only motivation, one of the only motivation that we have of taking classes here. It's the love and support that you guys show. So as I said, Unacademy wants to make sure that even if people cannot afford the subscription, they should be getting the access to right amount of knowledge, and that is why we are providing this content on YouTube absolutely free of cost. So make sure that you share it with all your friends so that more and more students can benefit out of this. Don't forget to press the bell icon and show your love and support by hitting that like button and sharing it with more and more people. Okay. So also the PDF of all the slides used in today's lecture would be available for download very, very soon. All right. And let me remind you one more time, those of you who are watching this JEE English channel regularly, if you want to not miss out on any of the lectures and schedules, then you should be connecting with us on the Telegram app. Use that link. Okay. Now, before I take your leave, one last time, let me remind you that this is my code RD Live. Use this code, get an additional 10% off on all your Unacademy subscription fees. If you like my lectures, if you think that you want me to guide you through your IIT journey, you can get yourself the Unacademy subscription using this code. Enroll in my courses, and I will try my best to make sure that you get to your dream college and your dream rank. All right. With that note, I will take your leave. I'll see you next time where we will carry forward this discussion. Okay. Till then, you guys can keep practicing hard and keep studying hard and take good care of yourselves. So that is it.